Hi, in this video we are going to talk about the theoretical background of knapsack problem, so let's get started. What is this problem? It is a problem in combinatorial optimization, and it is a very famous problem, by the way. So the problem is that given a set of items, each with a mass W and a value V, determine the number of each item to include in a collection or knapsack so that the total weight, capital M, is less than or equal to a given limit and the total value is as large as possible. So this is why it is called a knapsack problem, because it's like you have a knapsack and you have items, and of course a knapsack has some capacity, and you have to decide what items to include the knapsack. And of course you want to make some optimization, that you want to make sure that you are taking the most valuable items with you. The problem often arises in resource allocation where there are financial constraints, and it has lots of applications: finding the least wasteful way to cut raw materials, contest of investments and portfolios, seating contest of assets for asset-backed securitization, construction and scoring of tasks in which the task takers have a choice as to which questions they answer. And I heard one of my friends playing games on the internet. You can make a football team and you have to pay, I mean in real dollars, you have to pay for the players, and you have to decide what players to take for a given money. And it is a typical multiple constraint knapsack problem, and you can use algorithms in order to calculate the optimal solution. So if you know these algorithms well, I think you can pretty make sure that you will get enough money. So by the way, there are two problems concerning knapsack problem. The first is the divisible problem, and the second is the 0-1 knapsack problem. The divisible knapsack problem, if we can take fractions of the given items, then the greedy approach can be used. So sort the items according to their values. It can be done in ordo n log n, for example, with a merge sort. So this is the time complexity. Start with the item that is the most valuable and take as much as possible. Then try with the next item from our sorted list. This linear search has linear time complexity, of course, so the overall time complexity is equal to n log n. So we can solve the divisible knapsack problem quite fast without any heuristic, without any dynamic programming. You just have to use the greedy approach. Okay, but sometimes our problem is not divisible, and this is the 0-1 problem. In this case, we are not able to take fractions. We have to decide whether to take an item or not. So while the divisible problem is you can take, for example, as many gold with you as you can, here you have to decide whether to take the gold or not. And a greedy algorithm will not provide the optimal result. Another approach would be to sort by cost per unit weight and include from highest on down until knapsack is full, but it is not a good solution too. We have to use dynamic programming. So dynamic programming we have been talking about in the theoretical sections, so it solves larger problem by relating it to overlapping subproblems and then solves the subproblems. And of course we have to use some memoization that stores intermediate results, so though they aren't recomputed over and over again. And the solution to original problem is easily computed from the solutions to the subproblems. So this is the essence of dynamic programming. So knapsack with dynamic programming. We have to define subproblems. We have n items, so we have to make n decisions whether to take the item with given index or not. The subproblems are the following: the solution considering every possible combination of remaining items and remaining weights. We have a matrix, this S, with parameters I and W, the solution to the subproblem corresponding to the first I items and available weight W. We are going to see an example, it will be clear. Or in other words, SIV IW is the maximum cost of items that fit inside a knapsack of size W choosing from the first I items. We have to decide whether to take an item or not. So this is the essence of the 0-1 knapsack problem. So this is the subproblem. We have to use the math that mocks. We can make decisions. If we do not take the item, then this matrix SIW will be SI-1W. If we take the ith item, then our matrix will be the way I, which is the value of the ith item, plus the S with the parameters I-1 and the V W minus WI. Of course, we have to reduce the weight of the items we have been taking, but we are going to see an example. I know this matrix form has no sense in this form, okay, but it's very important that we are only considering the SI-1 W minus WI if it can fit in our knapsack. So if the W is greater or equal to the WI, so WI is the weight of the ith item, we can consider putting it in the knapsack. Of course, I think it's pretty straightforward if there is enough room for this item. If it's too heavy and it is not able to fit into our knapsack, of course we don't have to think about taking it or not, because we cannot take it. Okay, so in the next video we are going to solve a problem together, and I hope that you will get a good grasp on this matrix with I and W parameters. Thanks for watching.